Hello, so let's take a look at some spectral problems and work through the analysis of the infrared spectroscopy and the mass spectroscopy. So if we look at an overview of some of the main kinds of functional groups we can find, of course we've got things like alkenes with carbon-to-carbon double bonds. The double bond absorption of infrared radiation is usually around 1680 to 1640 wave numbers. That's a stretching vibration. There's also a stretching vibration for the carbon to hydrogen bond for a hydrogen which is attached to the carbon in the carbon to carbon double bond. That's normally a small to moderate peak, about 3080 to 3020 wave numbers. And then finally, there's usually a broad and fairly strong bending vibration for that same carbon to hydrogen bond, which is attached to the carbon to carbon double bond itself, usually somewhere between 1000 and 675. Most part is probably closer to 600 than it is to 1000. So we usually see these stretches for a alkene. Following on, we could also see alkynes. And of course, for those alkynes, we'll see the carbon to carbon triple bond, normally about 2260 to 2100. For the most part, the alkyne bond stretch is relatively small and occurs usually slightly below 2200. Above 2200 is where we see that similar stretching position for a nitrile carbon to nitrogen. But it can be up as high as a nitrile, just keep that in mind. We've got the carbon to hydrogen bond stretching when it's attached to the carbon to carbon triple bond. Of course, this is only for an alkyne bond which is on carbon 1 to carbon 2. If it's embedded in the chain somewhere, the stretch doesn't appear. And we also see that bending vibration again for the CH bond, somewhere between 700 and 600, usually moderate to strong. Keep in mind also, as we've said in the notes, if the alkyne is symmetrical, with the triple bond exactly in the middle of the molecule, giving us a mirror image plane, then quite often the triple bond doesn't appear. We also have aromatic molecules with carbon to carbon bond stretches, usually peaks of weak to moderate strength, one at about 1600 and one fairly close to 1500. There's sometimes another stretch about maybe the 1400 range as well. Sometimes all three peaks appear, sometimes two of them appear, and sometimes only one of them appears. Most commonly a peak of moderate strength around 1600. We also have the carbon to hydrogen bond stretch on the aromatic ring, usually just above 3000, similar to what we see with the alkene and the alkyne, although the alkyne is a bit further to the left around the 3300 range. We also have stretches for an alcohol, the OH bond itself, usually moderate to strong in the 3600 to 3000 range, so a very wide range. And usually it peaks at about 3300. And of course that main thing here is that the OH stretch is one of the broadest peaks we see. It looks like a huge big thumbprint on the left hand side of the spectra. We'll also see a carbon to oxygen bond ether link, like in the 1200 to 1000 range. It's usually one of the biggest peaks in this range, but of course it's difficult to determine below 1400. But if there isn't something there, then it might not be an alcohol. Of course, we also have the amines with our nitrogen to hydrogen bonds. I haven't put it on my picture here, but usually about 3300, and it's usually that crab claw effect with two peaks if it's NH2 or one peak if it's just an NH. We also have aldehydes and ketones with that carbon to oxygen bond occupying a broad range of 1760 down to 1670. Remember, it's a very strong peak, and if present is usually the strongest peak in the spectra, almost complete absorption of the infrared energy, and so a peak that almost goes down to zero transmission. It's usually above 1700, but it can be below 1700 if there's conjugation with a possibility of resonance with other pi bonds. Of course, if it's specifically an aldehyde rather than a ketone, we have that CH stretch attached to the carbonyl group, giving us distinctive CH stretches at about 2800 and about 2700 as well. That's well below the normal alkane range for a CH stretch, which is usually about 2900. So it is very distinctive, and it usually rules out a ketone and makes it specifically an aldehyde when those two peaks are there. Finally, nitriles, which has a moderate to weak peak in the 2200 range, usually a bit further left than what you would see for the alkyne peak. And again, that's fairly distinctive. If there is a peak in this range, it's probably either the nitrile or the alkyne. But to be sure, just check for other alkyne peaks, like the CH at 3300 and the bending CH at around 7600. If they are not there, then it's probably a nitrile group. So that covers most of the peaks at their relative positions and their relative strength as we see the peak at a particular position up and down on the page here. So let's look at an example. Here's an infrared spectra and accompanying mass spectra for a compound. And we've got a molecular ion peak at 128 with a couple of big distinctive peaks downfield with smaller fragments. The infrared only really has one distinctive peak at 1718. So what kind of compound could it be? Well, our main suspects with that carbonyl peak here would be either that it's a ketone with alkyl groups on either side, or maybe an aldehyde with a hydrogen on one side, or maybe it's some kind of carboxylic acid. So a CO peak, and it's the only peak there, so it really rules out the possibility of it being the aldehyde, because we're not seeing those peaks at 2700 and 2800 for the CH stretch, and it rules out the carboxylic acid, because if it was, we would have that broad peak centered around about 2800, overlapping the CH peaks, a broad OH peak for a carboxylic acid. It's not there, so it really means that this is a ketone. So it's not just about the peaks which are there, it's also about the peaks which are not there. So you'll have a short list of suspects, and you can usually rule out until there's only one kind of functionality left. Looking at the molar mass of 128, we can subtract for the oxygen, which is there, 16, so it leaves us with 112 grams of mass. We can then divide by 14 for the number of CH2 units, and that looks like the formula is C8H16O. We suspect it's a ketone, of course, and so although we might not know for sure which ketone it is, we can probably make an estimation of something like octan 2O. We get a bit of evidence from the mass spectroscopy which seems to back that up. If we look at some of the smaller fragments, we've got a peak at 113, which looks like we've had alpha cleavage on the left hand side with the mass dropping by exactly 15 units. That's what we'd expect for octan 2On with alpha cleavage on one side. We could also suspect alpha cleavage on the other side, that first carbon to carbon bond after the functional group, with the peak at 43. So it does look like the carbonyl group is specifically on carbon number 2, because of those two main peaks. But there's also a peak at 58, and what could that be? So for the ketones and aldehydes, if we just reimagine the molecule slightly different, imagine it curling around a bit like a tail, we can also imagine that there's a McLafferty rearrangement happening in the molecule. What do we mean by that? Well, of course, there's a hydrogen projecting off this carbon, and it's round about there, and that hydrogen feels an attraction to the oxygen here. So we can actually see a making and breaking of chemical bonds as this molecule rearranges to form these two fragments in the spectral analyzer. So the bond breaks here. Alright, let's go through this in order. The hydrogen, which was attached to the carbon here, makes a bond to the oxygen here. The pi electrons swing around here to maintain the oxygen's octet. That causes the accompanying carbon-to-carbon bond here to break, and the electrons, when that bond breaks, swing round to make the carbon-to-carbon double bond. It's what we call a McLafferty rearrangement, and this piece here explains the peak at 58. Quite often for a ketone or aldehyde, the tallest peak tends to be from this kind of McLafferty rearrangement. And then the peak at 70 here would be the alkene portion of the molecule that's left over. Looking at the second problem, again the main peaks have been pointed out for us. So the main suspects we would expect them to be would be alkyne because of that peak at 2160, but it's also relatively in the range for a nitrile. It's a bit more to the right, so probably a alkyne rather than a nitrile. The nitriles tend to be in the 2200 range. But the thought that it's an alkyne is further backed up by the peak at 3313, which is probably the carbon to hydrogen bond stretching for the hydrogen attached to the carbon triple bond. And also the peak at 627, which is very strong and very broad, which is characteristic of a bending vibration for a carbon to hydrogen bond which is attached to the alkyne. So we can rule out the nitrile as our product here and pretty much confirm that it's the alkyne. If we look at that molar mass of 96, we can divide by 14 for the number of CH2 units. It comes out neatly 6 times with a remainder of 12 units. We could most easily explain that 12 grams of mass as an extra carbon rather than any extra hydrogens. And so that formula C7H12 would best be explained as hept-1-ine. Let's look at our last problem, which also has 3 distinctive peaks. Again, if you want at home, take a look and see if you can work out the spectral analysis for yourself before we look at the answer. So the most distinctive peak to my eyes is that peak at about 3028. It's further to the left than we'd normally expect for a carbon to hydrogen stretch for an alkane, and that's usually only one of a few possible suspects when that happens. Could be an alkene, maybe an alkyne if there's some conjugation bringing the peak further to the right, or it could be a benzene ring. So if we look at the peaks together, it looks like that peak at 3028 is actually the carbon to hydrogen stretch for a carbon to carbon double bond like an alkene or an aromatic. But then the peaks at 1606 and 1498 look like the stretching vibrations for the carbon to carbon bonds in a benzene ring. It would rule out really the alkyne because we don't see anything at 2200, and rule out the alkene because we'd normally expect a stretching vibration for the double bond further to the left between 1680 to 1640. And we've also got the CH stretching overtones in the 2000 to 1600 range, which is again characteristic for a benzene ring. So it does look like we've got a benzene derivative. If we check the molar mass at 106, so we can rule those out, it's just a benzene derivative. Divide by 14 to work out the number of CH2 units, and it comes to about 7. And we've got a remaining mass of 8 to account for. If we use that together with 4 hydrogens, that gives us a mass of 12 to give us an extra carbon. So it looks like the chemical formula is actually C8H10. So it looks like a benzene derivative with 2 extra carbons, something like maybe ethylbenzene. If we look at some of the fragments, the first major peak after the molecular ion peak is at 91. That would be with the CH3 group on the end dropping off to give this reduced mass. And then also at the 77, looks like that methyl group or methylene group has then dropped off, dropping the mass by another 14. And finally peak at 65, that first carbon that was attached to the alkyl group, giving us that 65 peak as the ring itself breaks down.